Okay, so everybody's back and we're back in the shed. Today we're going to have a little look at multimeters. And we're going to look at the main types, which are digital multimeters and analog multimeters. Probably not so common these days. The digital multimeter is probably the most common type of multimeter you'll get. Why are they called multimeters? Basically, there are a number of meters in one case. So here we have an amp meter or current meter. We have a voltmeter that measures DC and AC. And we also have an ohm meter or continuity tester. Same on the digital, we have our voltages, both AC and DC. We have our continuity tester, and we have our amp meter over here, both AC and DC again. With a couple of extras, we've also got a temperature sensor and we've got a diode tester. So we're going to look at each of these meters individually and then actually put them through some tests and see what the readings are and come to some conclusions that maybe the analog meter is better for some type of jobs, maybe the digital multimeter is better for some type of jobs. Anyhow, we'll come back and have a look at the analog multimeter. Okay, so here we have our analog multimeter. This is a bit of history, I suppose, with this meter. I've had this meter now since I was a fourth year apprentice in 1979. They were released in 1979 and we were given one each at the factory where I did my apprenticeship at. This meter is still functioning and still gets used daily now on the hobby bench. Probably doesn't get used in industrial application like it used to, but it's certainly used quite a bit, and it's quite a handy little meter. Now, Hioki been making meters since about 1934, so it's actually a Japanese constructed meter. It's not Chinese, it's not an El Cheapo off Evil Bay. It's a quality Japanese instrument. The Hioki company were the ones that brought out what they call the taut band, which has a magnetic system in here to lock the pointer and thus makes it drop proof. And I've actually dropped this from about 3 or 4 meters up a ladder, and it survived, and its accuracy is still intact and still functions. Now here's our analog multimeter. For the purpose of this demonstration, when we do a resistance measurement, we're going to be using a resistance decade box, so we can dial up a predetermined resistance and see the measurement on the meter. And for the voltage measurement, I've got a variable DC power supply. We'll do the measurements on the DC voltage. The AC voltage works exactly the same. The only thing is I don't have a variable, or I don't have an AC voltage at the workbench here available at the moment, apart from the mains voltage, and I'm not going to plug this meter into the mains voltage because it doesn't have these appropriate safety ratings for today. So, and we'll go into that a little later on when we talk about what's the difference between a $10 multimeter and a $500 multimeter. Okay, so next step is to get the resistance decade box out, and then we'll go down here and we'll do some resistance measurements. We'll also do some continuity testing as well, which is very good for checking whether a switch works or which way the contacts in a switch switch. Because you can check the continuity, you can check whether the switch circuit is closed or whether it's open. And we'll demonstrate that after we've done the resistance tests. So I'll get the decade box out and off we go. So here we have our decade box set up. Down the bottom we can dial up different resistance values and we'll be able to actually read them on the meter. The decade box is set up so it gives you 1 ohms by 10 by 100 and by 1000. So we can measure some high resistances and we can measure some low resistances as well. Now if you notice, the meter is actually set to K ohms at the moment. We're going to move it to 1. Now if you notice, the needle has moved off the 0 mark. So one of the problems with an analog meter is every time you change the range, you've got to re-zero the meter. The decade box is set up so it's all on 0, so that means between these two terminals there is 0 ohms. So that should be a dead short, and it should read 0 ohms as well. So how we do that is this little dial knob here. We just adjust that, and if I can do that, we can actually wind it up and get the needle back to 0. Okay, so now some of these analog meters you'll also find will have a mirror backing the scale, and that's to get rid of the parallax error. When you have a look down when you look down on the needle, you can be looking from slightly different angles, so either from this side or from the other side, and this will give you an error in your reading. So if you look down and you can't see the needle, the reflection of the needle in the mirror, you know you're directly over the top of the needle. So you'll find some scales or some meters will actually have a mirror in the back as well, and that's what that's for. Okay, I think I hit the camera, so I'll hit the focus again and try and get it focused in. Okay, so now we're set on the 1 ohm scale. So if we start moving the 1 ohm needle up, you notice it's moved now off 0. And if we go up to 2, you'll notice it's reading 2 ohms, 3, 4, and as we wind it up, so the needle is changing. Now you notice the scale we're using on this one is the bottom of the green scale here. So for the 1 and by 10 readings, we use the bottom part of that scale, and for the K ohm readings we use the top, which is marked in K ohms, or 1000 ohm increments. Now you notice how much difficult this is compared to the digital one. That's the beauty about the digital multimeter, is it auto ranges and you don't have to worry about any of these selections. Okay, but we'll put this now back over onto the 1000 ohm scale, and as you see, the needle has now gone out of adjustment, so we need to readjust the needle back to 0, and if we wind our 1000 ohm value up, you'll see, there we go, it moves to the 1000, 2000, 3000, 4000, 5000, 6000, 7000, 8000, 9000, 10,000. Now you notice that the scale is not linear, so it doesn't go up in equal distances like say a tape measure or something. It's logarithmic, so it goes up in different values. So you see there the distance from 5000 ohms to 10,000 ohms is not the same distance as it is from 0 ohms to 5000 ohms. Okay, so beware of that when you're taking readings off this, that you can't approximate the measurement. You've actually got to look at the dial and the scale and see what it's saying. Okay, so that does it for resistance measurements with the device. What we'll look at now is continuity, which is probably the main thing that we'll use in model railroading. So we'll get rid of the box, and we'll move the meter down a bit further. And I might see if I can move the camera down and reposition it so we can see the meter a bit better. Now we've lowered the camera down a little bit so we can see the meter a bit better. And if I put the probes in front of the camera, you can see whether the circuit is open or closed. So at the moment, one of the main things that we need to find out in model railroading is which way a contact of a switch may be facing, whether it's open or whether it's closed, or whether that switch is in fact operating. So we need something that will tell us whether the circuit is closed or the circuit is opened. I always leave this on the high resistance range for doing these tests in the K ohms. And if we look at our meter at the moment, here's our probes. We have nothing between our probes, so we should have infinite resistance. And the needle, if you look at the k-ohm scale, is showing the infinite symbol, which means, which is basically an 8 lying on its side, and that means infinity. If I short the leads, these probes together, the needle should move to the 0 ohms scale. So I shorten them together, there we go, it goes to 0 ohms. It's telling us that there's no resistance in that circuit. So that's an open circuit, probes are apart, closed circuit, probes are together. So there you go. Open circuit, closed circuit. Now we'll come back later and we'll look at some voltage measurements. Now, to measure voltage, whether it be AC voltage or DC voltage with the analog meter, we need again to select the scale. As I said earlier with the resistance metering, it's a lot easier with the digital meter because it auto ranges and you don't have to think about what scale you're going to set the meter on. It's quite simple. If you don't know what the voltage is, you start off at the highest voltage and work your way down till you actually get the needle deflecting and giving you a reading. If you put it on the low voltage, say on 3 volts, and it's in fact 1000 volts that are going in there, you'll damage the meter by violently sending the needle right across to full scale deflection, which is when a needle on a meter reaches either ends of its scale, and it's known as full scale deflection. So by putting it down there, you could damage the meter. We know our voltage we're going to measure is going to be no more than about 30 volts, because that's all my DC power supply can provide. So if we take this down here and put it on the 30 volts DC scale, now what I've got here is the leads coming out of my variable power supply, and we're just going to clip them onto the probes of the multimeter. So we've put those on there, and you notice the needle has actually moved. So what voltage do we have here? We're on the 30 volt scale, so we use the 30 volt scale here, and if we go back across there, it's 5 volts DC, which is exactly what we had. And if you look at the power supply, yes, the power supply is set to 5 volts. So that's a correct reading. Now you notice if I wind the power supply up, this power supply goes to 30 volts, so you should be able to see what voltage it is. So at the moment now we got 15 volts. We're up to 20 volts. Remember, we're working on this scale here, the 30 volt scale. So let's wind the power supply back down, and we'll look for a smaller measurement, and we'll move to the 12 volt scale. So there we are on the 12 volt scale. So now we use this scale down underneath the 30. See, it goes from 0 to 12. If we wind our power supply up, there's 12 volts there. Now if I keep going, the needle keeps moving, and there's that full scale deflection, which is not good for the meter. So you need to bring it back from there. So there's our 12 volts. Now if I run that back down to a lower voltage, we'll actually move down now to the 3 volt scale. So we're on the 3 volt scale now, and I'll use a finer adjustment, and we can knock this down to virtually 1 volt. There it is there. Now you notice when measuring the voltage here, the needle is very stable, and this is one of the good things about an analog meter, is if you're looking for something that's pulsing or got an intermittent problem, an analog meter will most likely show that up, because you'll see the variations in the needle move rapidly between 2 points. With a digital multimeter, it's very hard to depict that unless you've got a bar graph on it. If you've just got the numbers on your digital multimeter, they will just flicker backwards and forwards, and you won't actually be able to see that fluctuation. if I change the voltmeter here, I'll put it up on a bigger scale. So if I change the voltmeter here and we got an intermittent problem, you'll actually see it because the needle will be moving. So there it is there. We've got a bit of a problem with the power supply. It's not giving us, and it's varying. Now, if that was looking on a digital multimeter, it would just be a matter of numbers changing on the screen, and it wouldn't have much meaning. Okay, so now, as I said before, the AC voltage measurement is done exactly the same as the DC voltage measurement. If you don't know what voltage it is, start at the highest voltage and work your way down till you get a meaningful reading. If you notice, the values on the DC and AC side are exactly the same, because we only have those three scales, 10, 12 and 30 to work with. So if there's no more questions, we'll move on. And I don't think there would be any questions because there's no way you can talk to me at the moment. Now, the next section we'll look at would be current measurement, but being as that's probably one of the least used measurements in model railway, it's mainly voltage and resistance and continuity we're looking at, we might pack the analog multimeter away and bring out the digital multimeter. Okay, so now we're going to look at resistance measurements using the digital multimeter. So we're all set up again. We'll hook these probes from the meter onto the decade resistance box. Everything's set to 0. Okay. Now we have our digital multimeter set up onto our resistance box. Now you notice here that the resistance box is all set to 0, yet the meter is registering 2 ohms. That will be the internal measurement of the actual wiring within the decade box and the resistance of these leads. If you notice, it's dropping down to 1.8 now, so that will vary quite often. Now, as you can see, our digital multimeter is far more accurate than the analog multimeter. So if we need to make precision accurate measurements, a digital device is always far better. Now, as I said before, our digital multimeter is a bit of a godsend to the industry, because you no longer have to think about ranges that you plug things into. So if you notice the voltage here, the voltage indicator here and here, there's no 30, 10, it's auto ranging. Same with the resistance. The resistance only has one position because it will auto range. So we'll see that if we dial up some resistance here. We can change some values. If we go up here, we can change some bigger values. So there you're seeing 100 ohms. Now, you notice underneath the digits, there's a bar graph appearing. So this meter would be quite good if you had an intermittent fault, because you could actually see that with the bar graph moving. But see what the numbers are doing? It's very hard to decipher whether that's an intermittent fault or whether it's just a bad read. And if we put up the 1000 ohm scale, if you notice, on the meter on this side, the ohm signal from just normal ohms will now change to 1000 ohms or k ohms. Naturally, if we were measuring meg ohms, that would also change up to meg ohms, but my resistance box down here doesn't do that. It only goes up to 1000 ohms. If I wind that up to 10, here we go, we got 9.96 thousand ohms, which is just about 10k. So, resistance measurements, to find a resistance value is quite easy with this device. All you do is connect it across your resistor and off it goes. You don't have to worry about scale, you don't have to do any of that. You just connect it and take the reading off the display. As with the analog one, we needed to look at continuity. So here's our two probes again, and what we'll do is I'll get rid of the decade box, and we'll come back when I've repositioned the meter and try and make it a bit bigger in the screen. Okay, there you go. I think that's a little bit bigger in the screen. Here's our two probes off our multimeter. Now at the moment, as you can see, the two probes are not touching each other, so therefore there is infinite resistance between the two, but our meter doesn't say that. It just says out of limits. The OL stands for out of limits. In other words, that resistance there is bigger than it can measure. A digital meter will never really say that there's infinite resistance there. It'll just say it's outside of the limits that the meter can measure. You do get meters that will measure up into higher resistance values, such as an insulation and continuity tester, which is used for testing high resistances in the megohms. And they're generally used by electricians to confirm that your electrical wiring doesn't have any shorts and the insulation is good. Now, the next thing is we're going to short these probes together. We short the probes together, and what happens? We're down to 0 ohms. Just about. Remember, it will always give you a bit of a resistance because it's measuring the internal resistance of the meter itself plus the resistance of the leads to the probes. So if we short them together, which we have here, we're going to get down to 0 ohms, which we've got. So when our contact is closed, we have 0 or very, very low resistance. When the contact is open, the meter will say out of limits, OL. Okay, so doing your continuity resistance reading, there you go, that's virtually a dead short, 0.4, half an ohm. Open it up, open limit. The other neat thing you can do with these meters is some of them will actually, in the continuity test, will actually have an audible signal. So if we push that, it clicked once, flashed, now you've got manual underneath there. If I shut the meter, it now makes a tone when the circuit's closed, and when the circuit's open, it doesn't make a tone. Open. Closed. Open. Closed. Open. So if you want to check the operation of a switch or the contact position of a switch, I recommend you use a digital meter and put the audio continuity tester on, and that will make life so much easier for you. If it's making a noise, the switch is closed. If it's not making a noise, the switch is open. Okay, now the next thing to do is to do some voltage measurements. As I said before, I only have a DC voltage source here, so we're going to put it onto this scale, which will now allow us to measure voltages. Now, as you can see, it's saying up there it's VDC. If I actually left it on there and connected it to an AC supply, this meter is smart enough it'll actually work that out and change it to AC without me having to change the dial. The other thing you can do with these meters as well is measure millivolts or very low voltage. So using our same power supply, we'll hook up the test probes to the voltage source, and as you can see, it's reading 6.3 volts, which is about correct. If I take this right the way down, now we're measuring 0.4 of a volt, or 400 millivolts. If If I can drop that any lower, it may change range and actually display in millivolts. No, I can't get it. Can't get any lower. So it'll actually drop down, and if we wind the voltage up, now notice there's a bar graph at the bottom, and at 3 volts it's halfway across the screen. So as we start to rise and it gets to its full value, it'll now reset and start again. See? So now 6 volts, you still got that bar graph. So if you were looking for a voltage that was there and then not there, you could actually see the bar graph move at the bottom, yet the numbers mean absolutely nothing to you. It's all gobbledygook. But by looking at the bar graph at the bottom, you can tell that the voltage is rising and falling. So back down to 0. Now, you notice that power supply is all set to 0 now, but it's still 0.183 of a volt there. That voltage is the static voltage in the air that it's actually picking up, because these leads on these meters, these cables, are acting like radio antennas. Any piece of copper that's floating in air will actually pick up radio antennas, but notice the voltage coming out of there is only in millivolts that it's picking up. So it's inconsequential to the big story or the big picture. Okay, now if we wanted to measure AC, we just move our dial down to AC. Now it's measuring the AC component of this power supply. If I actually wind it up, see, it's not actually changing. Now, the other thing you can do in the AC section, especially on higher end meters, is maybe measure the frequency. So if I push that button, it's telling me the frequency. Because it's a DC power supply, the frequency is 0. If this was powered into a mains device, the frequency would come up there as 50 Hertz. And if you notice, down below it also shows you the voltage it's actually measuring. Okay. Now this multimeter, if you notice at the top, it says it's a true RMS multimeter. What does RMS mean? Okay, very simple basic terms. RMS voltage, because AC voltage is a continuously changing waveform, the RMS value of that waveform will be the voltage that can do the equivalent amount of work in DC. So in other words, a 10 volt AC RMS supply will do the same amount of work as a 10 volt DC supply. So all the RMS voltage is the equivalent to what the DC voltage can do. So if we've got a 5 volt DC circuit, it will work on it will consume the same amount of energy as a 5 volt RMS AC voltage is producing. When they state voltages on devices, if it's AC and it just says 240 volts AC, that 240 volts is the RMS value. Unless otherwise stated, the voltage in AC supplies is always stated as RMS voltage. Okay, but that's basically what RMS means. It's the equivalent, it will do the equivalent amount of work as the same voltage DC circuit will do. Okay, so that's basically all we need to know about our digital multimeter here. It's very simple. They have a lot more functions. As you can see, this one actually will give you a temperature if you've got the thermocouple attachment into it. It's also got a diode testing function as well. The only other thing to address on these meters is current measurement. Now, in the world of model railways, current measurement is not a very big thing. We don't use it as much as we would use the continuity or the voltage measurements. They're by far the most common parts of the meter that we'd use in model railways, and that's why I've stayed with those two fields to measure. But as I said, it's a multimeter. There are multiple meters built into the device. Okay, the only last thing to talk about is, why can I buy a multimeter for $10 and why do I pay, as this one is, close to $500? The basically it's accuracy of the meter, quality of the components. Remember, these meters have tolerances, and as the climatic conditions change, it gets hotter or it gets cooler, so the accuracy of the meter will change. The more expensive the meter, the more tighter the tolerances are on the components, and therefore the less drift you'll get in the meter. If you look at a meter, it'll have an accuracy on there and it'll go, you should be looking for something no more than plus or minus 10%. I have seen meters that state that they're plus or minus 10%, and then when you actually do a comparison, they're around about 30% out. That's starting to get into the realms of unusable then. The main difference between a $10 and a $500 multimeter is its design safety features if you do something wrong. All the fluke meters, if you look on the back of them, there's a thing called the category rating, and there's category 1, 2, 3 and 4. Basically, if you use a category 1 meter, if you're repairing appliances. So if you're repairing a photocopier or a device inside a building, a computer or something like that, a category 1 meter would be fine. Category 2 allows you to measure mains voltages. So I would recommend that most model railroaders used at least a category 2 meter. If you're an electrician working in the field, you want at least category 3 rating. And if you work for Energex or the supply authorities, you at least want a category 4 rating. Now, if you read the back of a fluke meter or a Metrex meter or one of the more expensive brands, you'll actually see that it says on the back that this meter is designed and tested to meet the category ratings. When you look at cheaper meters, they won't say anything about the CAT ratings, or they may say that they have been designed to meet, but not actually.